The next trend we're going to discuss is something called ionization energy. Now, ionization energy is defined as the energy required to steal or to take an electron. Okay, to help you make sense of that, basically, ionization energy is the energy required to take an electron. Now, if you take an electron, what do you do to that atom? You ionize it. You make it into an ion because you now have an imbalanced number of electrons to its protons. So the name really makes sense. Ionization energy, the energy required to make it an ion by taking away its electron, okay? It's a way of measuring the strength at which the atom is holding on to its electrons, okay? Obviously, the electrons that are really far away on the higher energy levels, their ionization energy would be much lower. Whereas if we only have one or maybe two energy levels, then their ionization energy would be much higher because it's going to be closer to the nucleus and harder to take away, okay? The first thing they want us to do is write the equation for the ionization of sodium if the ionization energy, or IE, is equal to 496 kilojoules per mole. Okay, we're going to follow this example right here. So basically, A is our element. Sodium, the symbol for sodium is Na, not S or anything else, Na. And we're going to add the energy, again, the ionization energy, so 496 kilojoules per mole. Okay, then arrow, that means yield in chemistry, yields. An ion, so notice A plus, so that's going to be sodium with a +1 charge, plus its electron, which we just stole. So that's a way of showing, and not mathematically, just with the chemical equation, that sodium, if you were to add 496 kilojoules of energy per mole, you would be able to steal one of its electrons away from it, ionizing it into a sodium with a +1 charge. If we were to take 2 electrons, it would be a lot more amount of energy required, which they've already quantified and they know the number to that. But then it would be Na with a +2, and then we would have to add another electron over there. But again, that's just theory. All right, so the way that it works on the periodic table, again, it's all about a pattern that you have to learn how to recognize. The ionization energy on the periods, which are the rows, increase as you go to the right, and groups, which are columns, increases as you go up. So again, if I was to draw my little periodic table here, the one with the highest ionization energy is actually fluorine. Okay, it's fluorine. So again, it increases as you go up and to the right. So opposite the atomic radius, opposite, it basically increases as you go diagonal to the top right. That's the overall trend, diagonal up towards fluorine. Okay, now that we know that, it wants us to put the higher first ionization energy here. So I'm going to go ahead and project my periodic table. Let me go ahead and clean that up just a little bit because that's pretty confusing. Okay, there we go. So here's our periodic table. Again, we always need to look at this because otherwise, if you don't know where these elements are located, honestly, you have no idea how to do this. And if I didn't know where the elements were located, I wouldn't have any idea how to do this because again, it's not about memorizing which is higher first ionization energy. It has nothing to do with it. It's all about memorizing the trend, the pattern, if you know where they're located. And again, you have one of these. Therefore, if you could find the elements and you know the pattern, this is really not very difficult, okay? So the first one, again, at the very bottom left is SO. So there's S and O are located right there. Again, the trend goes this direction towards fluorine. So O is closer than S, and the reason is because the number of energy levels. S has 3 energy levels. O only has 2 energy levels because S, sulfur, has 3 energy levels. Like it says here, it would be easier to remove. So the easier or the higher ionization energy would be O, meaning it would be more difficult or more energy is required to steal its electron than sulfur. Sulfur would be easier to steal from. Oxygen would be harder to steal from, okay? All right, the next thing we're going to talk about again is, the next example I should say, is we have fluorine and neon. So fluorine and neon. It's actually harder to take away from fluorine, so it is more so. Now, that seems kind of weird because neon is a noble gas. It already has all 8 that it needs. So because, again, I told you that they are inert, they do not react, they do not want to interact with anybody, you'd think they'd be harder to steal from. But it's not really the case. Fluorine has 7 valence electrons. Again, notice it's in group 7. It has 7 valence electrons. Therefore, it's so close to getting to be a full outer energy level. Therefore, to steal from it is actually more difficult because it really doesn't want to give away another one, because then it'll have 7, and that's 2, or have 6, excuse me, then it'll be 2 away. So neon, although it is full, is a little bit easier to steal from than fluorine, because fluorine really, really is close to having its 8. So again, just remember, fluorine has the highest ionization energy, therefore it would have to be greater than even neon. The next one is fluorine and chlorine. This one's pretty easy because fluorine is the hardest and the highest, meaning the hardest to steal from. And again, it's not surprising because chlorine has 1 more energy level, therefore to steal from it would be a fair amount easier than, well, obviously fluorine. The next we have is nitrogen here. We have arsenic there, and then we have, well, fluorine. So again, that's obvious. Fluorine's the highest. The next most difficult or highest ionization energy would be nitrogen. That's going to be your number 2. And then arsenic with 2 more energy levels would be far easier to take from, meaning its ionization energy would be much lower. Less energy required to steal. Nitrogen much harder to steal from, and fluorine just a little bit more difficult than nitrogen. All right, the next one we have is chlorine. Let me go ahead and clean this. The next we have is chlorine, which is located right here. Then we have sulfur right there, and fluorine. Why do they keep putting fluorine here? I don't know. So obviously the hardest would be fluorine. The next would be chlorine. It has 1 more energy level, but it has also 7, just like fluorine. So it really doesn't want to give up any also. But sulfur, again, would be the next easiest, or the easiest of those 3. Okay? All right, so here's an overall pattern. If you guys want to take a look at that. Again, this is kind of the pattern. Notice again the trend there.